molarity relates moles of solute to liters of solution. And so this makes it really, really useful in chemistry where we're doing chemical reactions in an aqueous solution and we've got solutions that we're mixing together, and it's easy to measure the volume of the solution. And then if we know the concentration, we can calculate the number of moles. And so this is referred to as solution stoichiometry, where instead of doing grams to moles to moles to grams, we're going to use volume to moles to moles to grams. So what I told you is still true. You can always start with grams to moles to moles to grams. Anybody dreaming that yet? Grams to moles to moles to grams. Here, what we're going to do is instead of starting with a mass, we're going to start with a volume of solution. We convert that to amount of A in moles using the molarity. When we did mass to moles, we had to calculate the molar mass, right? Here we don't have to calculate molar masses because they tell us what the molarity is. And then at the end, moles to volume, again, that conversion factor is going to be the molarity. And so it's very similar to just doing grams to moles to grams. Now, sometimes you could end up starting with a mass and ending with a volume, or starting with a volume and ending with mass. I mean, there's like almost an infinite number of problems that could be asked about this. And that's why it's important to learn to understand the idea behind it, because then you can do all the problems instead of memorizing specific formulas, and then you've got an awful lot of stuff you have to keep in your head. And then you might get stumped by that one question I try to trick you with on an exam. So this is how we would do solution stoichiometry. What volume in milliliters of a 0.15 molar HNO3 solution will completely react with 35.7 milliliters of a 0.108 molar Na2CO3 solution according to the following balanced chemical equation? Again, we're reading the whole problem. We're going to highlight numbers. We're going to highlight the question. We want volume in milliliters there. And then just like with grams to moles and moles to grams, I'm going to use the balanced chemical equation to organize these numbers. So this is 0.150 molar HNO3. So I'll find HNO3 in the balanced chemical equation, and I'll write that concentration below it. But instead of the capital M, I'm going to write moles per liter, because that's what it means. And then we have 35.7 milliliters of, that's the sodium carbonate. So I'm going to write that under sodium carbonate, 35.7 milliliters. And then this is the concentration of that solution, 0.108 moles per liter of that solution. And then the question is, what is the volume of the HNO3 in milliliters? Volumes are almost always going to be in milliliters because milliliter is a more useful size, right? We don't usually do chemical reactions in the lab where the volume is in liters because that's just an awful lot. So we use milliliters a lot. So this is stoichiometry. This is not dilution, right? These kinds of numbers, we have two molarities and we have a volume, and that's what we had in that dilution problem, right? And so some people, I can do the dilution. No, we can't. Because in the dilution problem, we were starting with calcium chloride and we were ending with calcium chloride. This is involving a chemical reaction. There's a chemical equation given. I have a concentration of one substance and a concentration of a different substance. And what you miss if you use dilution here is you miss the mole ratio. If the mole ratio happens to be 1 to 1, you'll come up with the correct answer. But I guarantee you that the mole ratio will not be 1 to 1 on the exam because I know that students like to do that, and I want to make sure that you don't do that. So we're going to use unpause. I wish something would show up there when it happens so that you could tell me. Really, really hate that. Anyway, okay. So we have a volume here. These look like conversion factors, right? Moles per liter, moles per liter. Those are going to be conversion factors. So this is what I'm going to start with. That's not grams, right? So to use this conversion factor or this conversion factor, I need moles and liters. So that would make this liters to moles. And actually what we have is milliliters. And then at the end, they're asking us to find volume in milliliters. So we can go to liters and then to milliliters. We've done problems like this before where we had kilograms and kilograms, and we saw that those conversion factors canceled out. And so the people that are comfortable with that probably don't need me to do the example that way, so I'm not going to. So I'm going to kind of go with the middle road and show you how you can kind of cheat on one end but not the other. So we're going to do this. We're going to go liters to moles to moles to liters to milliliters. And we can do that by recognizing that 35.7 milliliters is the same as 35.7 times 10 to the minus 3 liters. Right? Because that prefix milli stands for times 10 to the minus 3. So we're just writing one or the other, whatever is convenient. So 35.7 times 10 to the minus 3 liters of Na2CO3. And then I'm going to go to moles, and to moles, and to liters. That wasn't right. To liters, and then to milliliters.
Are we going to have to, are all equations going to be balanced for us, or there's going to be some that will have to?
That's a great question. Are all of the chemical equations going to be balanced for you? No. On an exam, yes, they would be. Or it would be pointed out. Normally what will happen is I'm testing you on can you balance an equation, or I'm testing you on can you do the solution stoichiometry, right? Now the worksheets are another thing entirely. Yeah, there I'm pretty sure they're going to make you balance it and do the calculations, and maybe make it a limiting reactant problem as well. So part of the idea of the worksheets is that after you do the worksheets, the exam questions should seem easy. Okay, so those worksheet questions, some of them are really, really hard. Yeah. And I don't expect you to be able to do those by yourself. That's why if you're not getting the correct answer, you're supposed to text me. Okay, and some of you are doing a great job of that, and some people aren't. And so I went to grade worksheet 3, and a lot of them is like mostly green, and there's a couple of reds, and then I go look at your work, and it's like, oh yeah, you just typed it wrong, you're all good. And then there's other ones where it's mostly red. And I'm like, oh shoot, I made this mistake, and then I made the little mistake here, and they must have been so frustrated because they couldn't get the right answers. So if you're getting red on worksheets or on your digital lab reports, text me, okay? Because I want you to get the right answers. You're going to learn more getting the right answers. You're going to feel better about it. And bonus, it's easier for me to grade, right? So you're helping everybody by asking. Good question. Okay, so liters to moles to moles to liters to milliliters. Liters to moles. Oh, I'm trying to write with the eraser. Moles of, and here we do need to specify moles of what. Yeah, it doesn't fit in there very well. But if we don't label the moles, we're going to get mixed up. So here I've got my liters coming down here. got moles of sodium carbonate. Those are going to cancel out. And down here, I've got my moles of HNO3. And then down here, I'm going to have liters. I should cancel those. All the units, work those out first. Now we're going to go in and put in numbers. So moles per liter. This acts a lot like a molar mass, which was grams per mole, right? It's a relationship between moles and a quantity of stuff. So here we need moles per liter for the sodium carbonate. So that's this guy, 0.108. 0.108 moles for every liter. Of course, you know, there's just really not enough space here. Just kind of squeezing in there. And in the middle, we have mole ratio. And again, that's from the balanced chemical equation. 1 mole of sodium carbonate for every 2 moles of nitric acid. So 1 mole of sodium carbonate for every 2 moles of nitric acid. The next one is moles in liters again, and that's the concentration of the nitric acid. So 0.150 moles. Okay, this is just getting a little ridiculous. Just cheat and move things over. Well, even then, I didn't move one over far enough. Whatever. Some places, you know, like here, there's way too much room, and then over there, there's just not even close. And then milliliters to liters. Remember, milli stands for times 10 to the minus 3. I've got milli on one side, I've got times 10 to the minus 3 on the other side. 1 milliliter is 1 times 10 to the minus 3 liters. This is a conversion factor that we end up using a lot, and students sometimes get it backwards. And so if you think about this, what's bigger, a liter or a milliliter? A liter, right? A liter is like half of a 2-liter bottle of soda, right? And we've all used the 10 mil graduated cylinders, right? So a milliliter is like that tall, right? About that square, right? Little teeny tiny thing. So sometimes students will tell me that there's 1,000 liters in 1 milliliter. 500 soda bottles in this big. No, right? So watch out for that. It is true that there's 1,000 milliliters in a liter, and you can use that conversion if you want to, but just be careful that you don't put it in the wrong place. That's one of the reasons I don't use that, because this way, millis on one side, you write what it means on the other side, and we really don't have to think about it.
So should we just put the 1 on the prefix?
Yes. You put 1 with the prefix and 1 with the times 10 to the something that the prefix stands for. So you never have milli and the 10 to the something together. They're always on the opposite side. And I love things where I can say always. It always works, right? It's not necessarily the fastest or prettiest way, but it always works. I'll go with that. Yeah.
Where you have 2 moles over 1 times, what's that supposed to be? On top of the 0.15 moles of
Up here?
nitric,
Yeah, that would be a 1.
Oh, okay.
Again, I tried to write with the eraser. This would be a 1.
I never seen that symbol.
Oh, it looks like a triangle.
Yes,
Yeah.
a triangle.
It's
The liter that's canceled out. Yeah.
That's not looking at it.
Yeah, one liter, and then it canceled out with the next guy. Yeah. No, thank you for asking, because, I mean, things just sometimes look weird to us. And then it's important to ask and find out what the heck, right? Okay, so then just calculator, right? 35.7 EE negative 3. Yeah, I almost couldn't see the 0.108 there because it's so out of whack. Times 0.108 times 2 divided by 0.150 divided by 1 EE -3. If you're using your scientific notation button incorrectly, you're going to come up with an answer that's off by several powers of 10. So 3 sig figs, this should be 51.4 milliliters. If you're getting a much bigger number, you have an issue communicating with your calculator. And bring your calculator to me during lab, and I'll have a talk with it. And you you listen over my shoulder what I'm saying to it, and then you'll know how to treat it in the future. It's always the calculator's fault. Any questions? Here's another one. Consider the reaction 2A plus B goes to C. What is the limiting reactant if you mix equal volumes of a 1 molar solution of A and a 1 molar solution of B? This kind of question bothers a lot of students because they're like, I've figured out how to do the calculation, but you're not giving me enough numbers to actually do a calculation here. You're going to make me think about it?
But it said
Equal
equal volumes.
volumes.
So it's one, right?
Yeah, so I mean, if you really wanted to do a calculation, you could make up a number. Say, well, I'm going to pretend that the equal volumes are 1, whatever. But let's think about this. So if I have 1 molar A and 1 molar B, and I have equal volumes of both of them, what does that tell me about the number of moles of each of them? They're the same, right? So the moles of A in this mixture are equal to the moles of B. Okay, equal volumes of equal concentrations. In this reaction, which of these do I need more of? I need 2 A's for every B. So which one am I going to run out of first? Not B. I need 2 of the A's for every 1 B. Yeah, it's tricky, isn't it? Yeah, so let's just say we had 10 moles of each of these. So I use 2 moles of A to 1 mole of B, right? And I use another 2 moles of A to 1 mole of B, and 2 moles of A, blah, blah, blah. I should have made it a smaller number. So here, 2, 4, 6, 8, 10. There's all my moles of A gone. Every 2 moles of this used up 1. So I've only used up 5 moles of the B, right? So the limiting reactant then is going to be A. I don't usually ask questions like that on an exam, but those are good questions to answer because it helps you know if you have a decent idea of what's going on or not.